Hi, in today's video we're going to be talking about thermodynamics and kinetics. So first, let's look at a reaction where you have A and B and they are in equilibrium with each other. And so we use this reaction energy diagram where you have energy on the y-axis and reaction progress on the x-axis. So in this case you can see that A is a higher energy compound or version of the compound as B. So we call this energy difference, or when we're looking at this energy difference between the starting materials and products, this is a thermodynamic aspect of the chemical reaction that we're looking at. So we're looking at thermodynamics when we're looking at equilibrium. We often use, or we do always use, a capital K, the K equilibrium, or the equilibrium constant. So it's important to recognize that when we're talking about energy, we are talking about Gibbs free energy. And so Gibbs free energy is, and the difference of Gibbs free energy is defined as the Gibbs free energy of B minus the Gibbs free energy of A. And this gives us our delta G, and this is again our thermodynamic factor. So when we look at what delta G is, it's related to our KEQ. So it's related to this the equilibrium constant. And we can actually calculate Gibbs free energy using the KEQ. So you can use this equation, delta G equals negative 2.3 RT, so R is a constant, T is the temperature, log times KEQ. So I'm not going to ever ask you to do this equation in class, but a quick back of the envelope thing to know is that under standard temperature and pressure, so roughly room temperature, this 2.3 RT ends up equaling 6 kilojoules per mole. So what does that mean? Well, it means that at standard temperatures and pressures, which is most often how we operate or where we operate, for every 6 kilojoules per mole in difference of 6 kilojoules per mole for this energy level, there's going to be a 10-fold difference in concentrations. So if you were to measure a solution and you said that there are 10 times as many molecules of B as A, you'd say that there's a 6 kilojoule mole difference between A and B. Similarly, if I said that there's an energy difference of, let's say, 12 kilojoules per mole, you would know that there is a now 100-fold ratio of one of the compounds to the other. Again, it's a log scale, so for every 6 kilojoules per mole, there's another factor of 10 added in. And so remembering back from Gen Chem, delta G is also equal to the enthalpy, the delta H, minus the temperature times the entropy. And I know entropy is an important factor, but for many reactions in organic chemistry, this T delta S term ends up being about the same on each side of the equation, and so it's often very small. It's a small contributing factor. Whereas delta H, the enthalpy, is, for example, bond strengths and other factors like that, that ends up being a really important factor. So far we've been talking all about thermodynamics. Let's look at kinetics. So kinetics is when we have an energy barrier between A and B. And there's always going to be an energy barrier for any reaction. And so this energy barrier and the ability to go over this energy barrier is what we're thinking about in the context of kinetics. And we can refer to this barrier as the activation energy barrier, or the amount of energy that goes into getting over this barrier as the activation energy. So when we're thinking about kinetics, we're thinking about this little k, which is a rate constant, and this tells us we can calculate how fast we go from A to B looking at a rate constant. And that equation, again, the rate now, the speed at which you can go from A to B, or how much B you're producing over time, is directly equal to, in this case, the concentration of your starting materials, which I'm saying is A, times your rate constant. So if you have a high concentration of A, you're going to have a faster rate. As the reaction gets to the point where there's very little A left, well, the rate is going to become very, very small. Let's look at some energy diagrams and compare and contrast them. So in this case, we have two energy diagrams, and the one on the left, you would say, is favorable, where the starting material is higher energy than the product. So you end up having a negative delta G. Actually, before I get into that, I'd like to point out that the top of this energy barrier is called the transition state, and that's an exceedingly short-lived time in the molecule. It's just one vibration of the molecule, or less than one vibration of the molecule. So we call this point the transition state, and it's quite challenging to observe. You really need a very, very fast laser setup to observe that. It used to be said that you couldn't observe it, but technology has progressed. So going back to our delta G argument, so if we have a delta G where the products are lower energy than the starting materials, that means that delta G ends up being negative, and that means that the overall process is favorable. You can also say that process is exergonic, but I'll just stick with favorable. It's easier to say. If it ends up being a process where the starting materials are lower in energy than the products, that means that your delta G ends up being positive, and so the process is unfavorable or endogonic. Again, I'll just stick with unfavorable. So let's look at another case when we have a slightly more complicated reaction energy diagram going from A to B. We have this new little blip here in the middle. So in this case, you end up having two transition states, one highlighted as red and one highlighted as blue, and you have this new thing in the middle called an intermediate. And intermediates have quite varied lifetimes. They can be from nanoseconds to seconds to minutes. And on the way between A and B, we now call this intermediate, we say it's C. So I'll point out that this blue transition state is the highest activation energy barrier amongst this whole landscape. And this represents the rate determining step for the reaction. So again, the reaction is going to be determined by the highest transition state on this energy diagram. It's not necessarily that C, this little hill right here it's smaller than the hill from A over this red transition state, but the total transition state up to this blue one, that's the energy barrier that you have to think about in the context of a rate determining step. I hope you have lots of questions in class, and I look forward to fielding them in class and office hours. Have a great rest of your day. Bye.